this lecture, we will continue talking about elementary row operations. And for this purpose, I copied the definition of a matrix M to be in a row echelon form, and the three kind of row elementary transformations we have listed in the previous lecture. I added here also the lemma that says that when a matrix M is in a row echelon form, then its rank is very easily computable. It's just the number of non-zero rows. Remember that a row is just a vector, and here we are talking about non-zero vectors. So non-zero rows means non-zero rows as vectors. Okay, let's state first the main theorem. Any matrix can be reduced to 1 in row echelon form by means of row elementary operations. We're not going to prove this theorem, but we are going to show how to achieve that by means of row elementary operations, as the theorem has stated. Let's look at the example of the following matrix. This matrix has 3 rows and 4 columns. We will start from this matrix and operate with the row elementary transformations and see if we can get it to be in a row echelon form. Remember that row echelon form means that the number of zeros at the beginning of every row strictly increases as the row index increases. Okay, so that means that if we start from the first row, we have a certain number of zeros on the left. In this case is just 1. We have 1 0 here. And then if the matrix were in row echelon form, we should have a number of zeros in the second row that would strictly exceed 1. But we see that there are no zeros here on the left, so the number of zeros at the beginning of the second row is 0. So already looking at the first and the second row, we can clearly say that this matrix is not in a row echelon form. Now, how do we proceed in order to find a path that eventually will lead us to a matrix in a row echelon form? So the abstraction here for this matrix to be in a row echelon form is the fact that here we have a -1 instead of a 0. If we had a 0 here, then we would have 0, 0, and then 2, 1 in the second row. That means that the first 2 rows would be part of a matrix in a row echelon form. But we don't have a 0 here. And there is nothing we can actually do using the first row with the elementary row operations in order to make this -1 to be a 0. Because you see, if we multiply, well, you know, the first operation is switching between 2 rows, and this is what we are going to do. But if we forget about the first operation, the second operation involves multiplying a row by a non-zero scalar, so there is no way we can multiply the second row in order to make this -1 0. And unless we multiply, of course, by 0, but that is excluded by the condition. And then the third operation involves replacing, in this case, the second row with a row obtained by taking the first row, multiplying it by a scalar, and then summing it up with the second row. But again, the first row has 0 in the first entry, so if we multiply the first row by a non-zero scalar, well, by any scalar, we will still have 0 here at the beginning. And when we will sum up this new row, this new vector with the second row, it is impossible that we will be getting a 0 here. Okay, because we will simply adding a 0 to -1, and that is going always to be -1. So there is no way we can use this scalar by means of the third operation in order to kill this negative one. So that means that we cannot use the first row to somehow make the second row look like the one of a matrix in a row echelon form. So let's first apply the first elementary transformation in order to have as a first row the one starting with -1. Okay. So I have indicated here the operation. The operation is the kind of first kind of elementary operation, and it involves switching the order of the row 1 with the order row 2. We will be getting this matrix in which the second row becomes the first and the first row becomes the second. Okay, so now we are in a different position because the first row has no has 0 zeros here on the left, has no scalars. So the first scalar is -1, so there are no 0 scalar. And the second row has a 0 here on the left. So the first two rows now they are part of a matrix in a row echelon form. But the third row then is not, because in the third row we should have at least 2 zeros here on the left. Okay, but we have the number 2 and the number -1, so that this is not the case. However, this matrix looks better than the one before because we can actually use this -1 to kill this number 2. So if we kill this number 2 and we will make it 0, then it's still not in a row echelon form because we should have 2 zeros. -2 should become 0 and also the -1 should become 0. So that the number of zeros strictly increases from the row 1 to the row 2. But as a first step, we can actually use this -1 in order to kill these 2 by means of the operation 3. Let's see how we do it. Okay, so if we do an intermediate step, the intermediate step is to multiply the first row by -1. Okay, so we take -1 times R1 and we place this new row in row 1. Okay, so we multiply the first row by -1, and this is an operation of the kind 2. This is just to make a computation easier, nothing else. So we don't really need to... We could have performed this operation and the following one at once, but since it's the first example, let's just make them separate. So first we multiply the first row by -1 so that the leading coefficient, the leading scalar in this first row will be 1, and it will make the computation slightly easier. Next operation is the kind of 3, the operation of kind 3 that we mentioned before. So we can use this number 1 to kill this number 2, this coefficient 2 down in the third row. So the operation is, we take the row 3 and we sum to it row 1 multiply by a scalar. In this case is -2. So we take row 3 plus -2 times R1. So replacing a row Ri, in this case Ri is R3, by R3 plus alpha times Rj for a j, for some j. So in this case alpha is going to be -2 and Rj is going to be R1. The operation is as follows. So we take -2 multiplied by the first row and we sum it to the third row. We'll have 2 plus -2, which is 0. The coefficient -2 has been precisely found in order to have this number 1, this scalar 1, to kill these 2. Okay, therefore we need a -2 that multiplies the first row and then the summing it up with the row 3. Okay, so if we multiply -2 by this first row, we'll get -2 here, 0, plus 4, and then plus 2. -2 plus 2 is going to be 0, and here is 0. And then -1 plus -2 times 0 is 0, so is -1. Then 1 plus -2 times -2 is plus 4, which is 5. And then we have 0 plus -2 times -1, which is plus 2. As 2 is here. Now we see the situation is better than before. We have the first one again in row echelon form as before. The third one is not quite in the row echelon form with the previous two, because the number of zeros is just 1, and it is the same number of zeros as the second row. So we should have a strictly increasing number of zeros on the left, and in order to achieve that we have to kill this -1 and make it 0. Now we cannot use the first row, not just because here there is a 0 and we cannot multiply the first row by coefficient and then summing it up to kill this -1, but also because suppose that here were not 0, were some other coefficient. If with that coefficient we could kill -1 with an operation of the kind 3, but then we will most likely introduce again a non-zero coefficient here, which we just worked for making it 0. So we cannot use row 1 anymore, otherwise we will just destroy the work that we have done so far in order to make 0 the first coefficient of the last row. So we are going to use the second row to do this. Notice that the second row has a 0 here in front. So if we multiply the second row by any coefficient and we sum it with the third row, we are not going to ruin the work done so far to make 0 this first coefficient. It will always be 0 anyways. So we are going to use the second row, and we will find the coefficient to multiply the second row in order to kill -1. Just looking at this scalar here, the first non-zero scalar in the second row, which is -1. Therefore, the coefficient to multiply the second row to kill -1 is just -1, and we will be getting precisely this operation. So we'll take the third row, we sum a coefficient times the second row, and the coefficient is -1, so R3 minus R2, and we will be placing this new vector in the place of R3. Okay, so let's see, we have -1 minus -1 is 0, then we have 5 minus 1, which is 4, and then we have 2 minus 0, which is 2. And at this point, what do we have? Well, we have the first row, which has no zeros on the left, so the number of zeros is 0. The second row, which has 1 0 on the left, and the third row has 2 zeros on the left. So this is in the row echelon form. And the crucial part of the matrix to establish that this is in row echelon form is the placing of these zeros here on the left. We know now the rank of the matrix, so we knew by definition that the rank of this matrix would be at most 3, so at most the minimum between the number of rows and number of columns. Number of rows is 3, number of columns is 4, so the minimum is 3, so the maximum rank of this matrix would be 3. And in fact, here we have established that the rank of the matrix is indeed 3, because the number of rows that are non-zero is 3. All the rows are non-zero, so this is maximum rank. So this is in row echelon form, and by the remark, the lemma that we wrote at the beginning of the lecture, we see that this has rank 3. Rank equals 3. The last remark is the following. If we write T1, T2, T3, and T4, the 4 elementary transformations that we just used in the previous example, and we call M the initial matrix, this, and N the final matrix, the one in row echelon form, this. Then we have the following equality. So the final matrix can be obtained by M also through the following procedure. We take the identity matrix 3 by 3, which is denoted as ID3, and we apply to that matrix in the same order the same four elementary operations. So first the T1 applied to ID3 is denoted as T1, and then between the braces the matrix ID3, and then to that we apply T2, which is this, and then we apply T3, which is this, and then we apply T4, which is this. So we reduce the application of four elementary operations to the left multiplication of M by a certain matrix, and this is precisely the matrix we will be using. This is going to be helpful in many applications of elementary operations, and as we will see in future, also to find the inverse matrix of an invertible matrix.